Hello, math enthusiasts! Are you ready for today's discussion? Come and join as we venture into the world of mathematics. For today's discussion, I'll be teaching you and guiding you step by step through 6 important topics in integration. This include area computation, finding the centroid, volume computation, determining the length of the curve, area moment of inertia computation, and determining the work done in pumping of liquid.
Let's start with area computation.
When we say we're computing area in integral calculus, we mean we want to find the area of the region bounded between two curves. Imagine you have a shaded region on a graph, maybe between two curves or under one curve, and you want to find out how much space is inside that shade. Therefore, we use integration to do this by slicing the region into a very thin strip either vertically or horizontally. Let us imagine a region bounded between two curves. Both curves are written in the form of y is equal to f of x, meaning they are function of x. Suppose the top of the curve is y upper and the bottom of the curve is y lower. We look at the region between these two curves from x is equal to a to x is equal to b. To compute the area, we slice the region into two vertical rectangles. Each rectangle has a very small width, dx. The height of each rectangle is the distance from the bottom of the curve to the top of the curve. This height is found by subtracting the height, which is y upper minus y lower. So, the area of a thin rectangle is this. To get the area, we now add up all these strips from x is equal to a to x is equal to b. We do this by integrating. So our final formula is this. Now, let's consider the region from a different perspective. Suppose the curves are written in terms of x is equal to f of y, meaning the x values depend on y. This time, we slice the region into the horizontal rectangles. That the right curve is equal to x right and the left curve is equal to x left. We are now moving from the bottom at the region to the top. So, limits will go from y is equal to a and y is equal to b. Each strip has a very small height, which is dy. The width of the strip is the distance from the left curve to the right curve. This is founded by subtracting the width, which is equal to x right minus x left. The area of each horizontal strip is this. So, to find the total area, we integrate these strips from y is equal to a and y is equal to b. Therefore, our final formula is this.
Let's try an example. Find the area between two curves. 2y is equal to x squared and 2x is equal to y squared. First, we must plot our graph. The result of our graph is this, which is the up open parabola is the 2y is equal to x squared and the open right parabola is 2x is equal to y squared. To find the area between the two curves 2y is equal to x squared and 2x is equal to y squared, we begin by determining the points of intersection to set our limits of integration. First, we solve for x in terms of y from 2x is equal to y squared, giving x is equal to y squared over 2. Then, substituting this into 2y is equal to x squared leads to the equation 2y is equal to y squared over 2 squared. This becomes y raised to 4 over 4. Multiplying both sides by 4 to eliminate the factor, we get 8y is equal to y raised to 4, which simplifies to y times 8 minus y cubed is equal to 0. Solving this equation, we find the limits of integration are y is equal to 0 and y is equal to 2. Next, we set up the integral to compute the area between the two curves. Since we're integrating with respect to y, we convert both functions in terms of the x. The rightmost curve is x is equal to square root of 2y, and the leftmost is x is equal to y squared over 2. The horizontal distance between the curves at any value of y is therefore square root of 2y is equal to y squared over 2. So the area becomes a is equal to integral of 0 to 2 square root of 2y minus y squared over 2 dy. We then rewrite square root of 2y as 2 raised to 1 half and y raised to 1 half, making the integral into integral of 0 to 2 times 2 raised to 1 half y raised to 1 half minus y squared over 2 dy. Integrating term by term, we get 2 raised to 3 halves times y raised to 3 halves over 2 for the first term and y cubed over 6 for the second. Evaluating both at the limits from 0 to 2, we calculate it. So, our final answer is 4 over 3 square units. This is the total area between the two curves. Next, finding the centroid.
The centroid is the center of mass or balance point of an area. It tells us where the shapes would perfectly balance on the tip of a pencil. We'll find the coordinates of the centroid, which is the x-bar and y-bar, using vertical or horizontal strips depending on the shape. We can find the coordinates of the centroid using two main methods, which is the vertical strips or horizontal strips. We already know what is the formula of finding the area using vertical strips. Therefore, our problem now is what is the formula in finding the centroid using the vertical strips. Therefore, we want to compute two things, which is the x-bar, the average of x location, and the y-bar, the average of y location. To get the x-bar, we calculate the moment of each strip about the y-axis. Each strip is located at x, so we multiply x by the area of the strip. Therefore, our formula is this. For y-bar, we take the average of y position of each strips. Since the strip goes from the bottom to the top of the curve, the center of the strip is the average of the y values. Therefore, we has this. Then, we multiply it to the area of our vertical strips. Therefore, we have this formula. Similarly, if we're using horizontal strips, we integrate with respect to y instead of x. The width becomes the difference between the right and left curves, which is x right minus x left. Therefore, our formula for these horizontal strips in finding the centroid is this.
Let's try an example. Find the coordinates of the centroid x-bar and y-bar of the region bounded by the curve y is equal to x squared and the axis from x is equal to 0 to x is equal to 2. First, we must plot our graph first. So, this is our graph. To find the centroid x-bar and y-bar of the region bounded by the curve y is equal to x squared in the x-axis and vertical lines x is equal to 0 and x is equal to 2, we begin by finding the area under the curve. The area is given by a is equal to integral of 0 to 2 x squared dx. Then we integrate, which is we get x cubed over 3 and we evaluate from 0 to 2 gives us 8 over 3 square units. To find the x-bar, the x-coordinate of the centroid, we use the formula x bar is equal to 1 over a integral of a to b x times y upper minus y lower dx. Then we plug in the values, which is 1 over 8 over 3 integral of 0 to 2 x times x squared minus 0 dx. Then we simplify our equation. Therefore, we have 1 over 8 over 3 integral of 0 to 2 x cubed dx. Now, we integrate our equation. Therefore, we have 1 over 8 over 3 times x raised to 4 over 4. Now, we evaluate our limits. Therefore, we have 1 over 8 over 3 times 2 raised to 4 over 4 minus 0 raised to 4 over 4. Therefore, we get 3 over 2. Now, to find the y bar, the y coordinate of the centroid, we use the average of the top and bottom function, which is y bar is equal to 1 over a integral of a to b times y upper plus y lower over 2 times y upper minus y lower dx. Then, we simplify our equation. Therefore, we have y bar is equal to 1 over 2a integral of a to b y upper plus y lower times y upper minus y lower dx. Now, we plug in our values, which is 1 over 2 times 8 over 3 integral of 0 to 2 x squared plus 0 times x squared minus 0 dx. Then, we simplify our equation. Therefore, we have 1 over 2 times 8 over 3 integral of 0 to 2 x raised to 4 dx. Now, we integrate our equation. Therefore, we have 1 over 2 times 8 over 3 times x raised to 5 over 5. Then, we evaluate our equation. Therefore, our answer is 6 over 5. Next, volume computation.
In volume computation, using integration is useful when we revolve a flat region around an axis and we want to find the volume of the solid form. It's like spinning a shape around a stick to make a 3D object. There are three main methods, which is the desk method, the washer method, and the shell method. We'll explain here where they came from, how to use them, and solve a full example step by step. Imagine slicing the solid into thin circular discs. Each disc has a small thickness, which is the dx, if rotating around the x-axis. The radius of the disc come from the function, which is y is equal to f of x. Therefore, the volume of one disc is this. To find the total volume, we integrate. Therefore, our final formula is this. This is used when there is a gap between the region and the axis, creating a hole in the solid. Therefore, we subtract the small inner radius from the bigger outer radius. Therefore, the volume of one washer is this. To find the total volume of the washer, we use integration. Therefore, our final formula is this. In this method, we slice the region parallel to the axis of rotation. Let's say we rotate around the y-axis. Each strip is vertical and has a width of dx. When rotated, this forms a hollow cylindrical shell. Therefore, the volume of one shell is this. To solve the total volume of the shell, we use integration. Therefore, our final formula is this.
Let's try an example. Find the volume of the solid formed by rotating the region under y is equal to x squared from x is equal to 0 to x is equal to 2 about the x-axis. First, we must plot our graph. This is our graph. Since it states that it is a solid formed region, therefore, we are going to use this method. The formula of this method is b is equal to integral of a to b pi r squared dx. Our value of r is y. Since we have the value of y which is x squared, we plug in it to our r. And our limit is 0 to 2 since it's already said in our problem. So, we plug in now it to our formula. Therefore, we have v is equal to pi integral of 0 to 2 times x squared raised to 2 dx. Then, we simplify our equation. We have pi integral of 0 to 2 x raised to 4 dx. Now, we integrate our equation. We have pi times x raised to 5 over 5 from 0 to 2. Now, we evaluate our equation. Therefore, our final answer is 32 pi over 5 cubic units. Next, determining the length of the curve.
Finding the length of the curve using integration is useful in real-life problems like measuring the length of a winding road, the edge of a lake, or the path of a roller coaster. In calculus, we can't just use the ruler for curved lines. Instead, we break the curve into very thin straight line pieces and then adding up using integrals. Let's say we have a curve defined by a function y is equal to f of x. To get the total length, we imagine zooming in really close to the curve until a small part of it looks like a straight line. Using the Pythagorean theorem, the length ds of a small part of the curve is this. Then, we factor out dx to make it easier to integrate. Therefore, we have this. So, the total length from x is equal to a to x is equal to b become this formula.
Let's try an example. Find the length of the curve y is equal to x raised to 3 halves from x is equal to 0 to x is equal to 1. First, we must plot our graph. This is our graph. Our formula for length of the curve is s is equal to integral of a to b square root 1 plus dy over dx squared dx. First, we must find the value of dy over dx. To get this, we must get the derivative of our curve, which is the y is equal to x raised to 3 halves. The derivative of this is equal to dy is equal to 3 over 2x raised to 1 half dx. Then, we divide it by dx. Therefore, we have dy over dx is equal to 3 over 2x raised to 1 half. Then, our limit is from 0 to 1 since it already stated in our problem. Then, we plug in now it into our formula, which is integral of 0 to 1 square root 1 plus 3 over 2 x raised to 1 half squared dx. Now, we simplify our equation. We have integral of 0 to 1 square root 1 plus 9 over 2x dx. Now, let's integrate our equation. We can use u substitution. Therefore, our u is equal to 1 plus 9 over 4x. Then, our du is 9 over 4 dx. Therefore, our dx is 4 over 9 du. Then, Our limit for this u substitution is u is equal to 1 and u is equal to 13 over 4. We get this by plugging the x values to the u substitution, which is ru. That's why we get 1 and 13 over 4. Now, we plug in it to our formula, which is s is equal to integral of from 1 to 13 over 4 is square root of u times 4 over 9 du. Then, we simplify our equation. We have 4 over 9 integral of 1 to 13 over 4 is square root of u du. Then, we integrate our equation. We have 4 over 9 times 2u raised to 3 over 2 over 3 from 1 to 13 over 4. Now, we can substitute the value of ru, then evaluate it by our limits. Therefore, our length of the curve is 1.44. Next, area moment of inertia computation.
Area moment of inertia is very important in engineering, especially when dealing with how strong or stiff a beam is. In simple words, moment of inertia tells us how hard it is to bend a shape around an axis. The farther the area is from the axis, the more effect it has. The area moment of inertia, also called the second moment of area, is defined as about the x-axis, which is this, and about the y-axis is this, where dA is a small area element and y or x is the distance from the axis to the small strip. How did we get these formulas? Imagine a thin strip or slice of area at some distance from the axis. When the strip is farther from the axis, it contributes more the bending. That's why we multiply by distance squared, either x squared or y squared. If we are rotating or bending around the x-axis, we'll use the y squared because the distance is measured vertically. If we are bending around the y-axis, we use x squared since the distance is measured horizontally.
Let's try an example. Find the moment of inertia about the x-axis of the region bounded by y is equal to x from x is equal to 0 to x is equal to 3. First, we must plot our graph. Our graph is this. To find the area moment of inertia, we can use the formula Ix is equal to a to b y squared dx. The value of y is x and our limit is from 0 to 3 since it already stated in our problem. Then, we plug in it to our formula. Therefore, we have Ix is equal to integral of 0 to 3 x squared dx. Now, we integrate the equation. Therefore, we have x cubed over 3 from 0 to 3. Now, let's evaluate it to get the values. Therefore, our final answer for the area of moment of inertia is 9. Lastly, determining the work done in pumping of liquid.
Work in integral calculus, especially when pumping liquid out of a container, we encountered this in real life when emptying tanks, draining pools, or lifting water from wheels. Since different parts of the liquids are different depths, we use integration to add up the small amount of work done for each slice. The basic physics formula for work is this. But in pumping problems, different parts of the liquid are lifted to different heights. So instead, one force and one distance, we slice the liquid into thin, small layers and use integration to add up the small work done by each slice. Let's take a horizontal slice of liquid at a certain height y with a very small thickness dy. the volume of that slice is this. The mass of that small volume is this. The weight or force is this. The distance this slice is lifted is this. So, the small amount of work done to lift the slice is this. To find the total work, we integrate from the bottom of the liquid to the top. Therefore, our final formula for work is this.
Let's try an example. A tank is a cylinder of radius 2 meter and a height of 4 meter standing upright. It's full of water. How much work is required to pump all the water to the top? First, we must draw first our problem so that we can easily identify how to solve it. Here is our drawing. The volume of a thin horizontal slice of water at height y is given by dV is equal to pi r squared dy. Then, we plug in our r since it's stated in our problem which is 2 meter. Therefore, we have dV is equal to pi times 2 meter squared dy. Now, we solve for our weight or force, which is equal to density times gravity dV. Then, we plug in our values, which is 1,000 kilogram per cubic meter times 9.8 meter per second square times pi times 2 meters squared dy. Then, the value of our distance is 4 minus y. The formula for work is force times distance, but in integration, we use work is equal to integral of a to b density times gravity times dv times distance. Now, we have the values, we can plug in it now. Therefore, we have work is equal to integral of 0 to 4 times 1,000 times 9.8 times pi times 2 squared dy times 4 minus y. Then, we simplify our equation. Now, we have 39,200 pi integral of 0 to 4 minus y dy. Now, we integrate our equation. We have 39,200 pi times 4y minus y squared over 2 from 0 to 4. Then, we evaluate our equation. So, the work done to pump all the water to the top is 313,600 pi joules.
And that wraps up our lesson on the application of integrals. We've explored area, centroid, volume, arc length, moment of inertia, and work, all using the power of integration. If you made it this far, good job! You're not just memorizing formulas, you're learning how to think like a mathematician and apply these ideas to the real world. Don't forget to review each topic slowly and practice more examples on your own because we believe that repetition builds confidence. Always remember, calculus doesn't just solve problems. It reveals the invisible patterns that shape our world. If this video helped you, please leave a like, share it with your classmate, and consider subscribing for more calculus tutorials. See you next time. Bye-bye!